Thanks so much, everyone, for joining the call this afternoon. So I'll be presenting privacy-preserving federated learning for health sciences, joint work with faculty member Professor Xihe, Mazume, and David in collaboration with the AI engineering team, as well as the FL for Health team. So just to give an overview, in very short terms, federated learning is a form of decentralized machine learning, which asks everyone to leverage their local computing power to train models on their own individual data sets. And once they do that, to merge that into a global model. This is what federated learning is about. So how does federated learning model train a better sort of model in general? Well, it's because so many collaborators pool together their data sets. So this gives us an enlarged data set. So that allows us to create a better model through this form of training. Okay, you might ask, well, when you pool together the data, do you actually put them together physically? And the answer to that is actually no, because moving a large quantity of data across the internet to a central location to be able to do machine learning is very expensive. Just think of the communication that takes. Federated learning brings the model to each individual clients, and this allows them to not move the data, but just train it on their local data set and then move the model itself. So this is much better in terms of communication. So why should anybody consider federated learning? Well, because your private data stays with you. So this is one of the very important reasons why people are leveraging federated learning for health. As for example, the current FL for Health library that's under development. Okay, so we've mentioned so many beneficial points about federated learning. What about the risks to them? I'll mention a few. One of them is what happens that in the network of collaborators for federated learning, there are bad actors who try to do these adversarial actions and try to mess things up a little bit. And the risk number two is what happens, you're computing some sort of a model from your local data set, even though you don't move the data itself, but you actually do still upload the model. So, what kind of private information is contained in this model that you upload that an adversary could potentially leverage to, infer information about the private data set. So these are some of the risks that my work has helped to address. So first of all, in order to address this, there's two components. One is the privacy part and one is the security part. So the point of my work is to develop a federated learning system that is both private and secure and that can be used for healthcare machine learning. So this is my project statement. And the tools to address privacy and security are the following. The first is a formal framework to reason about privacy called differential privacy. And the second, to address security and to prevent adversaries from colluding the federated learning process, is called cryptography. Yeah. A little bit of a commercial interlude here. If you think our work is super fun, you might as well check out our GitHub page, the FL for Health library, and try to play around with it and give us feedback. Okay, so just to move on to our first part, the privacy aspect of this work. Oh, part of this slide didn't load. Hold on. Whoops, what just happened? Sorry. Can you guys see this slide properly? There's some issue with Google Slides.
It's like blurred out on the left.
Oh,
it's like a blue blurred question mark.
Okay. Let's see if this would work.
You can just describe it to us. It's not perfect, but
Okay. Does
there
that
you
look
go.
better?
Yes, there we go. Perfect.
Okay, so just to compare between centralized and federated learning, right? So what do you do when you have all the data together in one place and do just the centralized deep learning? Is basically you compute some sort of gradient and you follow the gradient to make sure your loss gets minimized. So this is the essentially the idea between a centralized learning, but In federated learning, everyone has their own individual database of private data, and each of them basically gets the model, a localized version of their model, and they can essentially train it on their own data set. So they end up having a bunch of gradient vectors. So which direction do you follow? Well, it turns out that all you do is you take the average of these directions, and then you follow the average direction of all of these localized gradient vectors. And this would help you to perform gradient descent on the global model. And essentially, when you do this kind of weighted average, you're weighting it by the fraction of data that your local database holds in relation to the entire collection of data sets held by all the clients together. So this is an important part about federated learning is how do you perform this stochastic gradient descent? Okay. Okay. So in the regular version of stochastic gradient descent, you essentially basically perform this kind of average, and then it gives you a direction that you multiply by some learning rate, and then you descend, right? But then, for private sort of stochastic gradient descent, what you actually do is a modified version of this vanilla stochastic gradient descent. There's two things you want to do. The first thing you want to do is you want to first clip the gradient. So you take each client's gradients and you scale it by a certain factor. That factor is 1 over the max of 1. And the norm, the true norm of your gradient vector divided by a certain scalar c. The effect of this so-called clipping is so that if the length of your gradient vector is less than c, it gets preserved. Nothing happens. But if it exceeds c, you would scale the vector so that its length is c exactly. So the effect is that once you scale everything, the length does not exceed c. And the point of this scaling to privacy is essentially you want to limit the contribution of each individual client. So you don't want to suddenly have one client contribute a super large sort of gradient that would influence the model a lot. You want to make sure that everybody has roughly sort of equal and bounded sort of contribution to the training. And the second part of privacy, private SGD is essentially you inject some sort of randomness, right? In this case, I basically say I want to inject a Gaussian noise that is centered, so mean 0, and then you want to have a certain variance that is related to the sort of clipping constant. So it helps you to inject this a little bit of noise into the mechanism so that you can help protect the privacy of the entire training process. And I'll elaborate on this in the future. So, okay, what if you did not have gradient, private stochastic gradient descent? There's things called gradient inversion attacks that allows you to take essentially a gradient vector and try to reconstruct aspects of your original training set. So here on the left is an example of this, right? It's basically taking the gradient, try to invert the process. So here on, for example, on the left side, you see the original picture, and then on the right side, you see the inverted sort of reconstruction that you can do using the gradient vector. And you see that they're actually pretty good. So if you did not consider privacy and give special treatment to the gradients, your adversary is able to essentially launch these inversion attacks and then basically gain a lot of information about your training set. And on the right side, I have another example, which is from a paper. You can see that using gradient inversion attacks, people are able to recover user data perfectly, like 0 error. So that is actually very significant. That's why we want to give special private treatments to the training process. And another illustration of this is, let's say, in a healthcare applications. So let's say you're doing some kind of medical imaging task, right? Let's say you have a certain sort of original image that you're performing this inferences on or training on. And then suppose that you do not give it any special treatment, people are able to launch reconstruction attacks based on the gradient inversion. And here's a kind of inverted image that you can have. And then there are two special treatments, which is relevant for the sort of work that I've been doing, is to prevent this kind of attack. So you can see that once you get special treatments and then you launch the attacks, you barely are able to reconstruct the effects. So yeah, this is why it's so important to give special treatments. And now I'd like to discuss how we can make privacy precise and quantifiable. Right now, I've just basically explained privacy very vaguely, but how can we make it very quantifiable and precise? So here's the technical intuition for differential privacy, the framework that we use to reason about private machine learning. So an algorithm output appears indistinguishable when your data is included or excluded from the algorithm input. So if you vary the algorithm's input by one data point, so this might be a data point attributed to a certain patient in a healthcare data set. Once you perform this variation of one data point, does the output of your algorithm vary drastically, or does it vary very little, almost indistinguishable when you include or exclude this input? So this is basically one way that we can reason about privacy, because if you had a removal or inclusion of a new data point and your algorithm output changed drastically, then this tells you a lot about the input data set, right? So this is not what we want. So we want a sort of privacy that makes it almost indistinguishable when you remove or include a data point. So differential privacy, then you can give a rough definition, is when an algorithm output appears indistinguishable when any single data record is included or excluded. And the consequence of a definition of privacy this way is so that it protects against any individual level information leakage. Okay, so recall that I've explained that the differential private SGD special treatment to the gradient descent process makes the algorithm differentially private according to this particular definition through noise injection. So how does it actually accomplish this? Well, actually, in general, what you want to do is you want to take an algorithm. This could be like a machine learning algorithm, such as stochastic gradient descent, or more general algorithms for training or inference. You would like to essentially add randomness to this algorithm so that even if you run the same algorithm on the same data set, there is still a little bit of variation in input due to this randomness. So that when you even alter a single data record and that causes the algorithm to vary, this kind of variation is roughly indistinguishable from the variation of the algorithm due to the random effect. So in general, this is how you would achieve differential privacy for an algorithm, and such algorithms are called private mechanisms.
Right.
Okay, so let's try to
Clear.
reason again
Okay,
about how the gradient descent is differentially private according to this definition that we just talked about. Well, first of all, there's a special treatment of limiting the effect of any single data point on the output of the mechanism. So if there's suddenly a very large gradient and you do not give this special effect, then that's going to drastically cause the output of the algorithm to change. So that is not private. That's why we want to clip this and put a sort of upper bound to prevent any single record from disproportionately influencing the output. And the second part we mentioned was to add randomness. So how does this mechanism get randomness, right? So there's actually two places where it gets randomness. So first of all, you added this random variable, right? So you perturb the original true gradient a little bit. So this adds a little randomness. And the second part of the randomness, which is more subtle, is actually comes from the stochastic part of the gradient descent. So you took a random sample among your entire data set, and then that particular way you chose the random sample introduces sort of stochasticity into the entire algorithm. So this actually second source of randomness is a much more subtle, and it's actually hard to account for, but it could be done. So these are the two sources of randomness. So I basically try to explain privacy in more precise terms. Now, how do we actually quantify privacy? So let me take you through that. Well, a private mechanism is kind of related to a randomized mechanism, and randomized mechanism is achieved by adding random variables to it, right? So it's a random variable is added to a mechanism to make it private, and the effect of that is it basically makes the output of your mechanism follow sort of probability distribution, right? So if your privacy definition is you want your output to look roughly indistinguishable, the way that you transfer that to statistical terms is you want to say the distributions are close in terms of KL divergence. So here it is. The equation is that you have this way of measuring the difference in two distributions, and it's called the KL divergence. And maybe you want to say that this KL divergence is very small, right? It's like under a certain small number epsilon. Okay. Well, actually, this is not quite exactly what we want, because KL divergence is something you can say about how close the two distributions are once you know the two distributions. So it kind of provides a statistical indistinguishability. But in practice, your adversaries observe events, not distributions, really. So just given an event, are you able to infer whether the algorithm is private or not? So maybe instead of looking at the inside, this entire thing, the KL divergence, maybe you just want to look at the random variable that the KL divergence is the expectation of. In other words, this thing in the inside of the expectation, we're going to call that the privacy loss random variable. So if your adversary looks at an event and maybe looks at this difference in the probability of those events associated with two different mechanisms, actually random variables, because they're random sort of random mechanisms evaluated at two data sets that differ by one data point. So this would measure the sort of privacy loss associated with observing that particular event. So this offers a sort of computational indistinguishability if you want this random variable to differ by less than some very small epsilon. So actually, this is the definition for pure differential privacy, is that you want for all events that your adversary is able to observe, you want this privacy random variable to be quite small. So comparatively, these two probabilities are very close together. But in practice, you often do not get this sort of very good pure differential privacy. This is able to be violated, but with a very small probability. So you may have this random variable, which looks as the difference of these two output probabilities. You may say, okay, this is not exactly under epsilon, but maybe it's going to fail or be greater than epsilon with some small probability delta. So this is something called approximate differential privacy. So the approximate differential privacy is essentially pure differential privacy that can fail for a small number of times. So when you sort of chuckle this equation into or inequality and try to rearrange it, the sort of definition you get is the standard one you see in many papers, which is the epsilon delta differential privacy. And that essentially says that if you have two data sets which differ by one single record, and then you look at the outputs of the random mechanism that you basically run on these data sets, okay, and there's associated probabilities, these probabilities are quite close. So most of the time it achieves the sort of pure differential privacy given by this parameter epsilon, but at some fraction of time delta, that is able to be violated here. And in practice, what we want to do is to choose this delta to be very small. So actually, you want this probability that pure differential privacy could fail to be very small. And actually, you want to choose that to be much lesser than 1 over n, n being the number of data points in your data set. And the reason why this choice is made is because then your pure differential privacy is going to fail for less than one client in expectation. So on average, we only get this sort of failure of pure differential privacy for less than one client. It doesn't mean that you're always going to get it for less than one client, but just on average. So that's why this kind of choice is made. Just to give some idea about what this quantification of privacy means. Well, if you take the output of this differentially private mechanism, for example, your DP-SGD, for example, you cannot basically process that output and uh, gain more information about the original data set than epsilon and delta, right? In other words, you cannot gain more information from a sort of a private mechanism. That is roughly what this means, but there's a very formal way to say precisely, and it's called the data processing inequality. And also, what's relevant for private mechanisms to deep learning is basically in the each stochastic gradient descent, that is considered one private mechanism. But when you perform multiple rounds of SG, that essentially entails a composition of many steps, many of these private mechanisms together. And there are also ways that you can compose these and try to reason about, what is the privacy of this composition of private mechanisms. And there are many ways that you can do this. Actually, the epsilon and delta, which is quite intuitive, is not a good way to account for this sort of composition. There are more advanced ways based on different sort of more elaborate versions of privacy definitions. Just to name a few, for example, concentrated DP, a zero concentrated DP, and a generalization of KL divergence is called the F divergence, and there is associated with FDP. There's also a third or yet another kind of DP called Rennie DP that is particularly good for accounting for privacy effect of the stochasticity of the stochastic gradient descent. So when you do that kind of random sampling to compute the stochastic gradient, the randomness of that effect in terms on privacy is best accounted in terms of a different type of privacy called Rennie differential privacy. So just to show you, there's a whole lot of zoo of different privacy definitions. So getting on to the second part, which is we talked about the privacy and we want to
Claire,
now talk about the security.
Claire,
Yeah.
I'm sorry to interrupt you. Would you mind wrapping it up? We're considerably over time.
Oh, I'm so sorry. Yeah, okay.
Okay.
Oh, I should have checked the time. Anyway, so for security, essentially what we want to do is to make sure that no adversary in our network is able to collude with the training process. And we kind of use a cryptographic technique to make sure that all of our inputs are encoded. When we send in the gradients for the server to compute an average gradient, we would like to leverage some of cryptography. Essentially, the effect is you basically ask everyone to add and sort of masking number. Like if your original input was 1 and -1, you want to add some number and then subtract some number. And then on the whole, you send these sort of sort of masked version of your input. And once you send that to the server, they can sum the sort of a masked version of the input, and they still get the right sum, the right sum of gradients. So this is like the technique. Okay, so just to show you what this is, if you add this sort of cryptographic technique along with differential privacy, then you get even more secure and private effects on your training process. Okay, so I guess I would not cover all of these. So just to mention some further directions, maybe we've talked about how to make the training process private and secure. What about the inference process? So what if, like people are trying to launch attacks on the inference phase, and then this might violate the privacy and security. So this is some sort of future directions that we might take. And thank you so much for your joining the call today.